Hello. In this video, we'll talk about using Matlab to perform mathematical operations. The first thing we'll talk about are Matlab's wide variety of arithmetic operators. As I mentioned in the last video, Matlab's optimized to perform matrix operations, and it has a complete set of operators which follow the rules of linear algebra. There are also a separate set of operators that perform what are called array-to-array operations. These operators perform operations between corresponding elements of arrays. Since we can do both matrix and array operations, each of which have their own rules about the sizes of the operands, it's important that we keep track of the sizes of all our arrays. Matlab provides several commands which allow us to determine the sizes of our arrays. After we do that, we'll talk briefly about the rules of operator precedence. These rules are the same as are used in most programming languages and handheld calculators, so we'll go over those quickly. Finally, we'll talk a little bit about Matlab's built-in functions. There are far too many of these functions to make any attempt to give a list of the available functions. What we'll do in this video is emphasize the general syntax used by the functions and do a couple of examples. This information, along with Matlab's help files, should give you the tools that you need to effectively use Matlab's functions. First, we'll go through a list of Matlab's arithmetic operators. The plus and minus signs, of course, perform addition and subtraction. Multiplication can be done with the asterisk symbol or with a period followed by an asterisk. This pattern of a dotted and an undotted operator will be true of all of our other operators. I'll explain the difference in a few minutes. There are four division operators: slash, dot slash, backslash, and dot backslash. Exponentiation is done with the caret symbol or with the caret symbol with a dot in front of it. Finally, transposing a matrix can be done with a single quote or with a dot and then a single quote. The operators without a dot in front of them perform matrix operations according to the rules of linear algebra. So the asterisk performs a matrix multiplication between two arrays. The slash and backslash operators do something that's kind of like division, but it involves a matrix inversion. The dotted operators, the operators with a dot in front of them, perform what are called array-to-array operations. In general, this means that the operations are performed between corresponding elements of the two arrays. First, I'll talk about the dotted operators. As I mentioned previously, the dotted commands perform what are called array operations, or maybe more descriptively, element-by-element operations. This simply means that the operations are performed between corresponding elements of the two arrays being operated on. This implies that the arrays have to be the same size. Also, the output array is the same size as the two operand arrays. There is an exception to the rule about operand sizes. If one of the operands is a scalar, the scalar operates on every element in the array. The output array is the same size as the array operand. Now we're going to do a couple of examples here on the board before moving on to performing the operations using Matlab. First, let's look at multiplying two arrays using dot times. The result is simply the product of the corresponding elements of the two arrays. So, in the first row and the first column, I take the two operands in that row and column, multiply them together to get the element that belongs in that row and column of the output. So 1 times 5 is 5. First row, second column is done the same way. 2 times 6 is 12. Moving down to the next row, 3 times 7 is 21, and 4 times 8 is 32. Dividing two arrays using dot slash is pretty much the same idea. The element in the first row and the first column is divided by the element in the first row and the first column, and that result is put in the first row and the first column of the output. Likewise, 2 divided by 6 is 0.3333, 3 divided by 7 is this, and 4 divided by 8 is 1/2. Finally, exponentiation is the same kind of idea. I raise the element in this matrix using dot times to the corresponding power in this matrix. 1 squared is 1, 2 to the 4th is 16, and so on and so forth. Let's do a few examples of the dotted operators. First, I'll set up a couple of arrays to work with. Let's make array A, say 1 space 2 space 3 semicolon 4 space 5 space 6. And then array B, 0 space 2 space 1 semicolon 4 space 0 space 3. Now, if we use dot times to multiply these two together, we get 0, 4, 3, 16, 0, and 18. Each element is the product of the corresponding elements in the operands. However, if we create another array, C, negative 2 space 1 semicolon 0 space 3, we can't multiply that by either of our previous arrays using the dot times multiplier. The sizes don't match. Now let's use dot slash to divide two arrays. Say B dot slash A. Each element in the result is the element in B divided by the corresponding element in A. Notice that the numerator is on what I think of as the uphill side of the slash. Now let's use dot backslash to divide B by A. The syntax is now A dot backslash B. B is still the numerator and it's still on the uphill side of the slash. We get the same result we got before. We multiply an array by a scalar. The scalar multiplies every element in the array. For example, 3 dot times A. Likewise, if we divide by a scalar, every element in the array gets operated on. Let's type A dot slash 2. To square every element in an array, A, we can just type A dot caret 2. Now let's talk about the undotted operators. As mentioned before, the operators without a dot perform matrix operations according to the rules of linear algebra. Before I do some examples and demos, I do want to note a few points. Addition and subtraction are the same whether done as matrices or arrays, so there's no dotted version of plus and minus. When multiplying two matrices, the inner matrix dimensions must match. The number of columns in the first matrix has to be the same as the number of rows in the second matrix. Division isn't really a matrix operation. When slash and backslash are used, they do look like a divide sign, but what's really done involves something that's more like a matrix inversion. Exponentiation multiplies a matrix by itself according to matrix multiplication rules, a specified number of times. Now on to some very brief reviews of linear algebra and some examples of using Matlab's matrix operators to implement these rules. First, let's really briefly review matrix multiplication. I want to multiply this matrix times this matrix. When multiplying matrices, to get to the element in the jth row and the kth column of your output, C sub jk, you multiply the elements in the jth row of the first matrix times the element in the kth column of the second matrix. Then you add them all up. So to get C sub jk, I take A sub j1 times b1k plus aj2 times b2k, so on and so forth, up to ajn times bnk. I can do this process with the times operator in Matlab. As an example, I'll multiply this matrix, 1, 2, 3, 4, times this matrix, 5, 6, 7, 8. To get the element in the first row in the first column, I multiply the first row of the first matrix times the elements in the first column of the second matrix and add them up. So it's 1 times 5 plus 2 times 7, which gives me 19. As another example, to get to the second row first column, I would multiply 3 times 5 plus 4 times 7 to get 43. As our next example, let's talk about something that looks like division, matrix inversion. Division, or Matlab slash and backslash operators, are generally used to solve systems of equations. Now, the typical way to write a system of equations is in this form. You have a matrix of coefficients A, which multiplies a column vector of unknowns x, that's set equal to a right-hand side column vector of coefficients B. Now, in order to solve for x, we pre-multiply both sides of this equation by A inverse. A inverse times A is an identity matrix, so that just leaves the x, so x is equal to A inverse times B. Now, Matlab chooses to implement this inversion process with something that looks like a division. A inverse to Matlab kind of looks like 1 over A. So we're multiplying 1 over A times B, or B divided by A. We have B divided by A. However, we're pre-multiplying by A inverse, so A shows up first, and we use the backslash operator. There's an alternate way to do this. You can use a row vector of unknowns. X times your matrix of coefficients A is equal to a row vector of coefficients B. If your equations are written in this form, you post-multiply both sides by A inverse, and if you solve for A, you get B times A inverse. Matlab solves this with a forward slash operator. You're still, in some sense, dividing B by A, but now A appears second in the expression because we're post-multiplying by the inverse of A. Now let's go through a few comments relative to our undotted operators. In multiplication between a scalar and an array, each element in the array is multiplied by the scalar, just as with dotted multiplication. As I mentioned already, addition and subtraction are the same process for array and matrix operations, so we only have one set of addition and subtraction operators. Dotted and undotted operators do exactly the same thing if both of the operands are scalars. There's no difference between the operators. Let's operate on some of our earlier arrays using undotted operators. First, let's remind ourselves of what's in the workspace. The matrix A is this, B is this, and C is this. We can't multiply A times B using the times operator. The inner dimensions don't match. We can, however, multiply C times A. And we can multiply A times the transpose of B. Matrices can be inverted using the inv command. For example, inv of C returns the inverse of our matrix C. If we multiply the inverse of a matrix times itself, we should come up with an identity matrix. So let's type C times ANS. By the same token, we can invert a matrix using the slash and backslash operators by typing EYE of 2, 2 by 2 identity matrix, slash C, or C backslash EYE of 2. It's really important to be able to keep track of the sizes of the arrays you're working with, and Matlab does provide a variety of commands to tell you how big your arrays are. Length returns the number of elements in the largest dimension of an array. This is really useful for one-dimensional arrays, where length will just return the number of elements in the array. The size command returns the number of rows and columns in that order in a two-dimensional array. And finally, if you just want to know the number of elements in an array, the numl command returns that information. To finish up our discussion of Matlab's operators, let's talk about the transpose operation. I left that one out earlier because transpose doesn't really have any meaning except as a matrix operation. However, regardless of that fact, we still have two transpose operators, quote and dot quote. Dot quote transposes the elements of an array. Quote with no dot also transposes the elements of an array, but it also takes the complex conjugate of the array at the same time. So if you have complex values in your array, quote transposes the elements and changes the sign on the imaginary parts of the elements. If the elements in the array are purely real, quote and dot quote do exactly the same thing. The order in which operations are done is according to the typical rules used by calculators and other programming languages. Exponentiation is done first. Multiplication and division are next. Addition and subtraction are last. Operations of the same precedence are done from left to right. You can override these rules by using parentheses. Operations within parentheses are done first. In the case of nested parentheses, inner sets of parentheses are done before outer sets of parentheses. Matlab has a bunch of built-in functions. I'll just provide the general syntax to use them and then do a couple of examples. Matlab's help files have complete lists of the functions that are available. Built-in functions are generally called using the syntax shown here. There are some exceptions to that rule, but I'm not going to go into those here. The function is always invoked by its function name. The list of input arguments to the function is contained in parentheses after the function name. The list is comma delimited. Parameters sent to the function are assigned by their order in this list rather than by their names. Typically, to the left of an assignment operator, there's a list of output arguments. The output arguments are contained in square brackets. The list is comma delimited, and as with the input arguments, the parameters are assigned by their order in the list, not the variable names used. The square brackets, by the way, are optional if only a single output argument is being returned from the function. As an example, let's evaluate the function y of t is equal to 3 times e to the minus t over 2 times the cosine of 4t. We'll evaluate this function over the range of time 0 to 10 seconds at intervals of 0.01 seconds. We need to keep track of a few things when we're doing this on Matlab. We have a vector of times with 1,001 points in it, so the cosine of 4 times t will also be a vector with 1,001 points, as will e to the minus t over 2. This isn't a problem with Matlab. If we send a vector to the functions that implement cosine and exponentials, we'll get a vector back that's the same size as the input argument. We need to multiply these two vectors together, point by point, so we'll need to use a dot times between the two of these. The scalar multiplications and divisions, this 3 times here, division by 2 here, and 4 times here, are all going to be operations between a scalar and an array. It won't matter whether we use dotted or undotted operators in these locations. First, let's set up the vector containing the times. I'll use colon notation to do this since we're given the spacing we want between time points. I'll name the variable t, give it a starting value of 0, an increment of 0.01, and a final value of 10. Now I'll implement the equation. I'm going to name my variable y and set it equal to 3 times exp of negative t over 2. exp is Matlab's function to evaluate polynomials. Use dot times to multiply this vector times cosine of 4 times t. Cos, as you may guess, is Matlab's cosine function. I'll follow this with a semicolon since I don't particularly want to see all these values scroll by, and press enter. Now my values are in the workspace. If I actually do want to see them, I can type the variable name and press enter. This isn't terribly informative though. There's really too much information here to be useful. If I'm interested in something specific, like the minimum or maximum value of the function, I can use Matlab's min and max functions to return these values. Min of y returns the smallest value in the y vector, and max of y returns the largest value in the y vector. But these don't really give me much of a feeling for what the overall function is doing either. Probably the best way to get a feeling for the function is to plot it. Luckily, that's really easy in Matlab. Just type the command plot and put the x and y data in that order as arguments to the function. So I'll type plot of t comma y so that the time data in the vector t is on the horizontal axis and the y data is on the vertical axis. Pretty cool and easy, right? I'll talk more about plotting in our next video. This video was mostly about using Matlab to perform mathematical operations. We introduced 12 arithmetic operators which fell into two categories, dotted and undotted operators. The dotted operators perform element by element operations, while the undotted versions perform matrix operations. Both sets of operators, though, can give special behavior if one or the other of the operators are scalars. We also talked briefly about operator precedence. The order in which operations are done by Matlab is consistent with most handheld calculators, so there shouldn't have been any surprises there. Finally, we talked about the syntax used by Matlab's built-in functions and did a quick example of how they work. At the very end of this video, we created a plot. Matlab has outstanding plotting capabilities with lots of options and abilities to customize plots. In our next video, I'll introduce some of the most useful and basic plotting capabilities.